All right, just to break up some of the monotony, I want to talk about the idea or question whether as to whether there are other life forms that exist in our solar system or our galaxy. Now, these are non-planetary life forms, and when considering the evolution of intelligent life in the entire universe, not just necessarily speaking about our Milky Way galaxy, scientists are confronted by two stupefying vastnesses: the improbability of the evolution of complex life and the prodigious expanses of the universe. In a universe with possibly 100 billion galaxies, each with billions of stars, even the least probable event may be expected to occur occasionally, even frequently, as our universe is increasingly expanding at an exponential rate in a unified way. Humans will probably never know whether or not the universe contains other life forms with a human level of intelligence. Even if there were thousands of other civilizations in the universe, other forms of photonic transmission require millions of years to travel among galaxies. Human observers would learn about these other civilizations only if they had evolved to the extent that they could have sent messages millions of years ago. And that is if and only if they had evolved to the extent that they could have sent messages millions of years ago while we were still evolving in Africa. And by now they may no longer exist. They might have gone extinct. So another problem is the ability to recognize a generalized transmission from another civilization. And this is the idea behind SETI, or SETI, which was the search for extraterrestrial intelligence. And it was also the idea behind the novel Contact, that was written by Carl Sagan, which we have discussed in other videos. One has to look everywhere for anything that might be a signal, perhaps an irregularity in what had been considered the lifeless throbbing of a pulsar. Because of the enormous resources that deep space communication and travel would require, the fact that humans have neither been visited nor contacted from outer space means very little. Science fiction speculates grandiose ideas about the possibility of travel through wormholes or through other dimensions, black holes, etc. But any travel through a wormhole or a black hole would probably result in the destructive scrambling of whatever that goes through it. The equation first formulated by astronomer Frank Drake, and the Drake equation, allows a rough estimate of how many planets with advanced civilizations might exist in the Milky Way galaxy. The equation consists of a series of probabilities: the fraction of stars that have planetary systems, or the number of planets in a system that have ecological conditions suitable for life, the probability that life will evolve, the probability that intelligence will evolve, and the probability that advanced technology will develop. The problem with these calculations lies with assigning values to the probabilities. Cosmologists disagree very greatly and widely on even the order of magnitude on some of them. There is little doubt that simple life could be widespread in the universe. Bacteria and archaebacteria, which is old bacteria on Earth, survive in a tremendous variety of circumstances that humans would consider destructive to life. Any conceivable bacterial life might require a solid planet with water, but there might be billions of such planets in the universe, and many of them might have life that resembles bacteria. Bacterial life forms may have evolved even on Mars, in our own solar system. However, the conditions that would allow the evolution of complex life forms in our planetary system beyond the bacterial stage might be vanishingly rare. In order for complex life to evolve on a planet, the planet must have relative stability for a long period of time. The emergence of complex life on the planet Earth was preceded by nearly 3 billion years of microbial evolution. How likely is the existence of other planets which, like the Earth, have had billions of years of relatively stable conditions? Well, this depends on the answers to the questions such as the following: how typical is the galaxy in which humans live? It is true that there are a lot of galaxies, 200 billion or more. The first deep field photographs from the Hubble Space Telescope in 1995 showed 1,500 galaxies from an area of deep space just 1/30th the area of the full moon. However, the Milky Way galaxy seems to be an unusually calm place to live. Gamma ray bursts from colliding neutron stars would destroy any life for many hundreds of light years around. Perhaps life in an entire galaxy. Of course, these bursts are very common enough in the universe that Earth should be hit by one of them every 200 million years. And again, these are gamma rays. But Earth has apparently not experienced any such radiation during the entire 3.5 billion years of life on this planet and 4.5 billion years of its existence. And in a sense, this is very scary. However, the Milky Way galaxy is a disk galaxy. It says disk, but it's more like a spiral galaxy. And it has orderly revolutions of stars. Of course, many of galaxies are elliptical galaxies, which have less stars orbits that are stable and whose stars experience many collisions. The Milky Way galaxy, however, has had relatively few stellar collisions and their attendant bursts of radiation. This has contributed to a long period of stable conditions that have allowed complex and intelligent life to live and to evolve on Earth. How typical is the solar system? Well, the sun and its planets appear to be very unusual in the Milky Way galaxy for reasons such as these. Number one, the habitable zone. The solar system is in the habitable zone of the Milky Way galaxy. And so that means that our solar system is in a zone within our galaxy that is habitable. If the sun were nearer to the center of the galaxy, all the stars would be very close together, and the sun would be dangerously close to many neutron stars and black holes. If the sun were near the edge of the galaxy, it may have produced few or no atoms that are larger than helium. And secondly, the size of the sun. Many stars are giants and burn out as quickly as 10 million years rather than the 10 billion that the sun will persist for us. 10 million years would not be enough time for complex life to evolve. And so many stars are hotter than the sun and would produce much ultraviolet radiation, which would in turn destroy life on its planetary surface or its planets. Now, many stars are small enough that they just convert hydrogen to helium, perhaps. But this is mostly what is happening in the sun now. However, the supernova, or the exploding stars that produced the solar system, generated many heavier elements. Because of this, according to geologists Peter Ward and Donald Brownlee, the sun has a 25% greater amount of heavy elements than a typical star its size. Thirdly, the stability of the sun. We've talked about the habitable zone, the size of the sun, now the stability of the sun. Many stars fluctuate in energy output. In contrast, the sun has been mild and stable, not producing the bursts of energy that could easily wipe out advanced life forms. Binary star systems are very common. For example, 2/3 of sun-sized stars are in binary or multiple groups. But complex life could not evolve on planets associated with binary systems because climatic conditions would be very unstable. And fourthly, there is the rarity of asteroids. Early in the history of the solar system, the Earth, Moon, and Mars, for example, were bombarded by asteroids. This bombardment stopped about 4 billion years ago. The first evidence of sediments on Earth comes from this time, when the Earth cooled down and the oceans formed, and part of the reason this bombardment stopped is that Jupiter has so much gravity that it has stabilized the asteroid belt and licked up many comets and asteroids from the solar system. Jupiter is just near enough to clear away asteroids from the Earth's path, but far enough away not to bother the Earth. Jupiter disturbs just a few asteroids into the path of the Earth, punctuating the history of life, but not often enough to destroy life. And so it punctuates the history of life. And what I'm referring to there are the mass extinctions. There are 5. Now, the permanent extinction is my favorite. Nevertheless, fifthly, the stability of planetary orbits. As of the year 2007, in the month of January, 199 planets had been detected that revolve around other stars. The same Doppler effect that causes the redshift of expanding universe also shows that these stars are being tugged along by the gravity of other planets going around them. The sizes and the distances of these planets from their suns can be calculated. If the residual variation shows a pattern, it can be assumed that the star has 2 or more planets. In the year 2005, a photograph of a large gaseous planet around a distant star was published. It may be possible, or rather actually impossible, to detect planets as small as the Earth around other stars. Either by the Doppler effect or photographically, the planets are so far detected that frequently hot Jupiters as big and gaseous as Jupiter close to the star perhaps represent a failed binary system. Such huge planets would destabilize the orbits of smaller planets, causing them to crash into a large planet, into a star, or be thrown into interstellar space. A solar system of hot Jupiters would be very unstable, and any Earth-like planets would certainly experience wild swings of climate change which would prevent the evolution of complex life. The eccentricity, or the departure from a circular orbit of the Earth, is only 0.0167, which is just enough to produce climatic effects. Some of the planets detected around other stars have an eccentricity, and again, departure from a circular orbit, as high as 0.93. Such planets as these, even if otherwise suitable, would have wild swings of climate that would prevent the evolution of complex life. Sixthly, the availability of comets. Comets may have played an important role in bringing water to the primordial Earth. How can scientists know whether other solar systems even have comets? The Oort cloud extends halfway to the next star, which is 2 light years into outer space. Some of those comets may be as likely to go to Proxima Centauri as to the Sun. Based on chemical analyses, the comets known in our solar system seem to be from the Oort cloud and Kuiper belt. Apparently, there are no comets from Proxima Centauri coming into the solar system, suggesting that Proxima Centauri has nothing that corresponds to the Oort cloud. The star Beta Pictoris, or Beta Pictoris, appears to have comets falling into it based on bursts of different colors of light. But how typical is this of solar systems? All right, and finally, we have the seventh thing to tell us how typical solar systems are, and why the planets appear to be very unusual in our galaxy. So here's another reason. The moon. The moon stabilizes the 23-degree tilt of the Earth. This stable tilt is what causes the regular alternation of seasons. And again, I'll just talk about the wind, for example. The reason why we have wind is because of fluctuations within the Earth's temperature, and then that also is connected within disturbances within the Earth's magnetic field, and that's what causes wind is the Earth's magnetic field and fluctuations with the temperature. Anyway, the 23-degree tilt of Earth, all right, is stabilized by the moon. All right, this stable tilt is what causes the regular alternation of seasons. Billions of years ago, the moon was closer and the Earth spun faster, resulting in extreme winds. Again, like I said, the moon has been moving away from the Earth, and the Earth's rotation has been slowing down, so that winds are not as deadly as they once were. So the moon has allowed the Earth to have a stable conditions for long enough that complex life has evolved, and of course the Earth's rotation is now a lot slower, and as we have said, the moon is now a lot more distant from the Earth. Now, at this point, a bigger or smaller moon or multiple moons would be unlikely to produce this effect. Now, therefore, solar systems like the one in which humans live, suitable for the evolution of complex and intelligent life, might be very rare in this or any other galaxy, extremely rare. But how typical is a place like Earth? The Earth may be a very unusual planet in the Milky Way or any other galaxy, but we do not know because we have only basically discovered the frontiers of our own galaxy, in our solar system, not to mention our own ocean. Well, how typical is Earth? Well, I have 3 things to say on this. Chemical composition of the Earth. Most known planets from other solar systems are gas planets. But if the solid planets were like many asteroids, which have a great deal of carbon and water, then the Earth would have either a massive greenhouse effect from carbon dioxide emission, or would have been completely covered with deep oceans, not having the shallow waters that appear necessary for the evolution of life. Secondly, the size of the Earth. If the Earth had been a little smaller, it would by now have been completely cooled and lost its magnetic field. This would have allowed cosmic radiation to rip away the atmosphere and water and life. This appears to be what happened on the planet of Mars. On a larger planet, gravitation would be so strong that complex life might not be possible. And so, even though the Romans named their god of war, Mars, after the planet of Mars, nevertheless, I don't think they will be fighting anyone on Mars until we find that there are civilizations on these other planets. Nevertheless, on a larger planet, gravitation would be so strong that complex life might not be possible. On a larger planet as well, all geological forms might collapse underneath an ocean. Not only would there be no terrestrial life, but also no erosion of nutrients into the ocean. And as a result of that, the entire ocean would be nutrient poor. And as a result of that, just as the middle of the ocean on Earth is today. And of course, habitable zone of the solar system. All right, this is the third thing. Within the solar system, Earth is in just the right place. Again, we've talked about that earlier. The only planet in the habitable zone, in fact, if the Earth were 1% further away from the sun, it would experience a runaway ice age. If it were, and probably go back to the snowball planet, or snowball Earth. If it were 5% closer, it would experience a runaway greenhouse effect sometime during its history. If the Earth were closer to a smaller star, the star's gravity would hold the Earth in an orbit in which one side would always face the sun, just as the moon always faces the Earth. Under such conditions, one side of the Earth would burn up, and the other side of the Earth would freeze, and then extremely strong winds would result. So you'd have one side of the planet extremely hot, one side of the planet extremely cold, and then you'd have extreme strong wind on the whole planet. So, as some observers have said, humans would thank their lucky star, but also their extremely lucky solar system and moon. Without the concatenation of all these unlikely events, the Earth would have had an extremely unstable history, losing its oceans or fluctuating in temperature so great that only bacterial life could have survived. On a cosmological scale, even the nearly complete freezing of the Earth that occurred most recently about 700 million years ago is a mild occurrence. According to Peter Ward and Donald Brownlee, when you consider all of these factors, it is possible that the Earth is the only planet that has been stable enough for complex life to evolve. even in the entire universe. At the very least, they claim the universe is not like Star Trek, full of humanoids with humans can make contact. Some people have used these very same data to claim that the Earth has been prepared for our arrival by a higher intelligence. And of course, you might want to look at the anthropic principle. However, such a principle is unnecessary. But while it is unlikely for all of these lucky things to have happened right here in this part of this galaxy, it could very well be that humans exist and think about such things in this place and not somewhere else, simply because this place is where the luck happened to occur. And at the same time, it might also mean that the rest of the universe, even if chock full of bacteria, is a very lonely place for creatures with higher intelligence. For further reading, there is George Basala's Civilized Life in the Universe, subtitle, Scientists on Intelligent Extraterrestrials. Conway Morris, or Simon Conway Morris, his book Life Solutions, or Life Solution, with the subtitle Inevitable Humans in a Lonely Universe. Randall Jackson's Planet Quest. This is an article with the subtitle The Search for Another Planet. Again, the first one's by Oxford University Press, second by Cambridge, third by the California Institute of Technology, and the fourth reading would be Carl Sagan's Cosmos, and then Peter D. Ward and Donald Brownlee's book titled Rare Earth, with the subtitle Why Complex Life is Uncommon in the Universe. And again, that is published in New York by Copernicus Press. And so we have just discovered information in regard to speciation in our planetary systems, our galaxy, and the universe as a whole. We talked about the stability of planetary orbits. We discussed the availability of comets, the moon, how typical Earth is, chemical compositions of the Earth, the size of the Earth, the habitable zone of our solar system. And hope this has been exciting to you. I hope you enjoy it if you're watching it, and stay tuned. We're going to go back into our Origin of Life series. I wanted to do this one around the same time that I did the Origin of Life, because I wanted to understand about life in the universe in general, even though the playlist is more concerned about life specifically originating on our planet.